a few, maybe 1,000 atoms, something like that. If you think about discrete clusters, ignore proteins, you know. But the biggest thing that somebody's made, sort of ex situ, I think about 56 metals. It might be 120, I've forgotten. But then there's quite a big gap to 2 nanometers, because 2 nanometers is 1,000 metal atoms. And in that region, I think that there's a lot of people interested in, Richard Catlow's been doing some interesting work on modelling structures in that size, and we've started talking about trying to make things and do some work to characterise them. So there's that range. So you come on board. I showed you a 2 nanometer, and I was talking to Paul Alvisatos last week at a meeting, and we both sort of agreed that's the smallest we ever get, is about 2, where you get little spheres. What's the biggest you can get with these methods? 12. And then, actually, what happens is that the surface energy starts to drop off, and so the things then want to be bulk, and so they'll break off and do surfaces. Where you can see it most spectacularly, I didn't bring the slides today, is in gold. Because in gold, we see very interesting behaviour where it's a slightly lower temperature system, and you actually see breakout. So you can do it under slightly different conditions, and suddenly, it'll go from being 5 nanometer to 7 to 8, and then it goes critical, and you get all kinds of little different crystalline shapes, and it's growing crystals. It doesn't care where it is; it's ignoring all that surface stuff. So I would say it's 2 to 10 nanometers. I'd be pushed if somebody said make me a nice 10 nanometer sphere. I'd probably say no. 8, yes. And rods, the length of rods, it's 5 nanometers with maybe up to 20 long, I would say.
Above 10 nanometers, you wouldn't see the same photoluminescence.
Oh, well, the photoluminescence effects depends on the bore radius of the material you're working in. So, in fact, you've got the opposite problem, because let me get this right, one of the things that people will be quite interested in is modestly modified indium arsenide and gallium arsenide indium phosphide. And in fact, 5 nanometers is too small. What you really want is about 12 nanometers, because the bore radius is about 20. Whereas cadmium selenide is about 15, and so that you get nice control. So in fact, it depends on how big the bore radius is, really, for the material. So some materials, actually, see, the nice thing about cadmium selenide and why all the work is on it is because the size you can control gives you across the visible region. People would love to be able to do, say, gallium arsenide or indium phosphide and bring it back across the visible, and in fact into the near infrared, but you can't control the sizes well at the sizes that you need. And also, 3.5s are very difficult. I mean, I've got a complete lecture on 3.5 nanomaterials, but that's not this. It's all about synthesis,
Fantastic. There are no more questions. I'll ask you all to join me in thanking Paul for a very interesting lecture on quantum dots and nanoparticles and problems associated with their synthesis and some solutions to that. And just draw your attention to next month's seminar, which will be on the 7th of July by Professor Chalice from Nottingham. So, thanks, Paul.